Hello, my name is Lauren Ulbrich, and for my poster presentation, I'm going to be talking about my research on using potassium-40 to study the radiogenic heating of exoplanets. Potassium-40 is one of several isotopes found in the Earth's mantle that helps with the internal heating of the planet due to heat let off through radioactive decay. This internal heating is thought to be a factor in hosting life as we know it for a few reasons, due to the fact that the liquid mantle allows for tectonic activity. This tectonic activity is important because it helps regulate the greenhouse gases in the atmosphere, specifically CO2, allowing for the surface to stay within a habitable temperature zone. Also, at areas where tectonic plates meet, studies have found nutrients in the surrounding rock and ocean that are necessary for life, making these areas possible hotspots for life creation. It is easy to see why this heating is so important on Earth, and it is thought that the planets created in similar conditions to Earth may contain these same isotopes needed to sustain radiogenic heating. That is why it is important to study the nucleosynthesis of potassium-40, because the amount of potassium-40 in a planet is critical to the amount of internal heating of a planet. One of the ways that potassium-40 is destroyed in a star is through the potassium-40 N-alpha chlorine-37 reaction. This reaction is the focus of my study. The motivation for my research comes from a recent study on the radiogenic heating of exoplanets and a discrepancy found in the destruction rate of potassium-40. In simulations done on the creation and evolution of exoplanets, potassium-40 was found to have a profound effect on the internal heating of exoplanets, specifically at the beginning of a planet's lifetime. In a star, potassium-40 is destroyed in two ways: the potassium-40 N-alpha chlorine-37 reaction I mentioned earlier, and the potassium-40 Np-argon-40 reaction. The rates of these reactions is important to know because the more potassium-40 that is destroyed in a star, the less will be available once a planet forms from the resulting nebula after the star dies. Recently, the potassium-40 Np-argon-40 reaction was constrained, suggesting a 10% decrease in potassium-40 within 100,000 years, a relatively small timescale compared to the lifetime of a star. My research aims to similarly constrain the potassium-40 N-alpha chlorine-37 reaction rate. So far, according to my reaction network calculations, when the potassium-40 N-alpha chlorine-37 reaction rate is altered by a factor of 2, there is a noticeable effect on the production of potassium-40, a hopeful sign for our future experiment. The experiment constraining the N-alpha reaction will be performed at the Edwards Accelerator Laboratory at Ohio University. In this experiment, the chlorine-37 alpha N potassium-40 reaction rate will be measured. A potassium chloride target with an adequate amount of chlorine-37 will be used, with a gold foil backing and aluminum frame. A 6 MeV alpha beam will be fired at the target, however due to energy loss, it will react at around 5 MeV. From the results found at the experiment, the potassium-40 N-alpha chlorine-37 reaction can be extrapolated. In preparation for this experiment, I calculated some of the reaction kinematics. The two graphs that are shown here represent the expected neutron energies we will detect during our experiment as a function of the neutron angle. The left graph shows the neutron energies for the chlorine-37 alpha N reaction, and the right graph shows the neutron energies of the potential contaminants of the reaction. For the contaminants, I looked at all the stable isotopes of chlorine and potassium, because they are both found in our target, as well as stable aluminum isotopes, just in case the beam is off-centered and hits the frame. For chlorine-35 and potassium-39, although they are both the most abundant isotopes for their respective element, their Q values for their alpha N reactions are too negative, and there isn't enough energy in this reaction for either to be a potential contaminant. Furthermore, looking at the respective neutron energies of the potential contaminants, all of their energies are higher than the energies for the chlorine-37 alpha N reaction, meaning the final results will be easily separatable. For my future work, as I stated before, the reaction rate for the chlorine-37 alpha N potassium-40 rate will be obtained at the Edwards Accelerator Lab. This experiment is planned to run in early 2021. Once the reaction rate is obtained, the potassium-40 N-alpha chlorine-37 reaction rate can be constrained and put into my reaction network calculation to identify any differences or discrepancies. From these results, a galactic chemical evolution model will be used to calculate how the new reaction rate affects the amount of potassium-40 in Earth-like exoplanets. That concludes the summary of my research on the effects of potassium-40 on the radiogenic heating of exoplanets. I hope you enjoyed, and if you have any questions or comments, feel free to email me using the contact information below.